Hello all, welcome to second lecture on Laplace transforms. In this we'll see the very important and very basic property of Laplace transform called the linear property, which states that Laplace transform of a into f of t plus b into g of t is equal to a into Laplace transform of f of t plus b into Laplace transform of g of t. The proof is very simple, which goes like this. We know that Laplace transform of f of t is integral or 0 to infinity e power minus st into f of t dt. Now in place of f of t, let us take a times f of t plus b times g of t. So that Laplace transform of a times f of t plus b times g of t is integral or 0 to infinity e power minus st into a times f of t plus b times g of t. Now if you multiply e power minus st with a into f of t and b into g of t, we get integral 0 to infinity e power minus st into a into f of t dt plus integral of 0 to infinity e power minus st b into g of t dt. Now we can take out a outside because a is a constant, we take it outside, and similarly in the second integral b is constant, so we can take b outside the integral. Then we get a times integral 0 to infinity e power minus st into f of t dt plus b times integral 0 to infinity e power minus st into g of t dt. And integral 0 to infinity e power minus st into f of t dt is Laplace transform of f of t. And here integral 0 to infinity e power minus st into g of t is Laplace transform of g of t. Therefore, we get a into L of f of t plus b into g of L of g of t, which proves the linear property for Laplace transform. Now let us evaluate Laplace transform of some elementary functions. If one is aware of this Laplace transform of these elementary functions, it will be easy for anyone to find Laplace transform of some bigger functions. So first we prove Laplace transform of 1 is given by 1 by s. Let us prove this. Laplace transform of f of t is integral or 0 to infinity e power minus st f of t dt. Now to find Laplace transform of 1, in place of f of t we take 1. Then we get L of 1 is integral 0 to infinity e power minus st into 1 dt. That is integral 0 to infinity e power minus st dt, which is equals to e power minus st by minus s within the limit 0 to infinity, because we know that integral e power at dt is e power at by a. So in this integral, in place of a we have minus s, therefore the integral e power minus st is e power minus st by minus s. Now if we apply the limits, upper limit is infinity, and we know that e power minus infinity is 0 and e power 0 is 1. So if we substitute the limits there, we get 0 minus 1 by denominator is minus s. After that we get it as 1 by s. Therefore Laplace transform of 1 is 1 by s. Now using linear property we can note this point. L of k, Laplace transform of a constant k, is equals to k times L of 1, because k is a constant here, and using linear property of Laplace transform, k can be taken outside. So we get k times L of 1, and because L of 1 is 1 by s, this is equals to k by s. So Laplace transform of a constant k is nothing but k by s. Now the second Laplace transform is L of e power at. L of e power at is 1 by s minus a. Let us look how L of e power at is 1 by s minus a. Again consider the Laplace transform of f of t, and in place of f of t we substitute e power at. Then we get L of e power at as integral 0 to infinity e power minus st into e power at dt, which is equals to integral 0 to infinity e power minus of s minus a into t, because e power minus st into e power at can be written as e power minus st plus at, and if we take out minus t common, then we get e power minus t into s minus a. So that is why we wrote here e power minus of s minus a into t. And integral of e power minus of s minus a into t dt is e power minus of s minus a into t divided by minus of s minus a within the limit 0 to infinity. And if we substitute limits, the upper limit is infinity. So in place of t, if we substitute infinity, we get e power minus infinity, which is 0, and minus lower limit is t is 0. So if we substitute 0 in place of t, we get e power 0, that is 1, and the denominator is minus of s minus a. So 0 minus 1 by minus of s minus a gives 1 by s minus a. Therefore, L of e power at, Laplace transform of e power at is 1 by s minus a. That is, for example, say Laplace transform of e power 2t is 1 by s minus 2. Laplace transform of e power 5 by 2t is 1 by s minus 5 by 2. Then what is L of e power minus at? That is, if we put minus a in place of a, we get 1 by s minus of minus a, that is 1 by s plus a. So Laplace transform of e power minus at is 1 by s plus a. For example, say Laplace transform of e power minus 5t is 1 by s plus 5. Laplace transform of e power minus t by 2 is 1 by s plus a 1 by 2. Now let us go further. Laplace transform of sine at is given by a by s square plus a square. Consider Laplace transform of f of t, and in place of f of t, let us write sine at. Then we get L of sine at is integral 0 to infinity e power minus st into sine at dt. So now to evaluate this integral, we use the formula integral e power ax into sine bx is equals to e power ax by a square plus b square into a sine bx minus b cos bx. Here in this integral, a is minus s and b is equals to a. So if we use this formula and if we substitute ab values, we get e power minus st by s square plus a square into minus s sin at minus a cos at in the limits 0 to infinity. Now let us substitute the limit. Upper limit is infinity here. So if we substitute infinity in place of t, e power minus infinity becomes 0. So after substitution of upper limit, the value is 0 minus, if we substitute lower limit 0, e power 0 becomes 1 and sine 0 becomes 0 and cos 0 becomes 1. Therefore, after substitution of limits, we get 0 minus 1 by s square plus a square into a, which is equals to a by s square plus a square. I think there is a small typing mistake here. Here in place of minus, here I should write plus here, make a correction. Plus 1 by s square plus a square into a, that is a by s square plus a square. Therefore, Laplace transform of sine at is given by a by s square plus a square. Now, Laplace transform of cos at is s by s square plus a square. The proof goes in a similar lines as Laplace transform of sine at. Now, you can try to prove the Laplace transform of cos at as s by s square plus a square. It is left as an exercise. Next, we go for Laplace transform of sine h at, sine hyperbolic function at, is a by s square minus a square. Again we start with the definition of Laplace transform, and in place of f of t we write sine h at. So L of sine h at is integral 0 to infinity e power minus st into sine h at, and we know that sine hx is e power x minus e power minus x by 2. Therefore, in place of sine h at, we write e power at minus e power minus at by 2. Now, if we multiply the terms, e power we take outside a 1 by 2 and multiply e power minus st into e power at and e power minus st into e power minus at. Then we get 1 by 2 times integral 0 to infinity e power minus st into e power at dt minus integral 0 to infinity e power minus st into e power minus at dt. That is equals to 1 by 2 times integral 0 to infinity e power minus of s minus a into t dt minus integral 0 to infinity e power minus of s plus a into t dt, which is equals to 1 by 2 times e power minus of s minus a into t by minus of s minus a minus e power minus of s plus a into t by minus of s plus a. And if we substitute limits, we get 0 minus of 1 by s minus a minus 1 by s plus a, which after simplification we get 1 by 2 times 1 by s minus a minus 1 by s plus a, and we after simplification we get this as a by s square minus a square. Therefore, Laplace transform of sine hat is given by a by s square minus a square. Now can you guess what is Laplace transform of cos hat? It is s by s square minus a square, and you can easily prove it similar as above. So in this lecture we derived Laplace transform of some elementary functions. Let us recall them again. Laplace transform of 1 is 1 by s. Laplace transform of e power at is 1 by s minus a. Laplace transform of sin at is a by s square plus a square. Laplace transform of cos at is s by s square plus a square. Laplace transform of sin hat is a by s square minus a square, and Laplace transform of cos hat is s by s square minus a square. So with this we'll stop this lecture here, and in the next lecture we'll continue deriving Laplace transform of some other elementary functions. Keep learning till then. Thank you.